Good evening, ladies and gentlemen, and welcome to the Hubble Space Telescope Public Lecture Series. As I hope to be always every month, although, as you know, this year I've been on a lot of travel. I am your host, Dr. Frank Summers of the Office of Public Outreach. If you did not get one on your way in, over on the table, you can get one on your way out. We have our beautiful Hubble picture lithographs, and tonight is an oldie but a goodie, one of the favorites from 2009, the Butterfly Nebula. Now, I will actually tell you the truth, this isn't really the Butterfly Nebula, it's the Bug Nebula. But in our press release, we said, hey, it looks a lot like a butterfly. The press called it the Butterfly Nebula, and the name is stuck. So this is something that got renamed by a press release. If you want to know more than just trivia about it, if you want to know some science about it, turn it over on the back, and we have approximately 330 words, because I write some of these, and when I'm given it, it says, Frank, you have 330 words, and that's all you have to write on the back, and information about it. Grab one on the way out. Our talk tonight, Greg Snyder, studying virtual universes with supercomputer simulations. This is going to be a high-tech extravaganza, and he gave me his keynote file. It had 700 megabytes of visual goodness in it. So I'm expecting some really cool movies because, hey, if you do simulations, you gotta do the cool movies to attract attention. But there's also fantastic science because I've seen some of the results from this work. Upcoming now, next month, we are voting on the first Tuesday, right? Everyone shake your head, yes. At least those who are 18 and of voting age and are if you're not registered, go out and get registered. I don't care which party you vote for or what candidate you vote for, just get out and exercise your democratic right and vote on November 4th. Then remember, and you have your little I voted sticker, maybe we'll get I went to astronomy lecture stickers for the next weekend because we're going to have Mark Kamiankowski talking a telegram from the early universe. And let me tell you, folks, this is one of the world experts on the cosmic microwave background. The remnant radiation from the Big Bang comes from 500,000 years after the Big Bang. Mark, I worked with him much too long ago, 1997, 98, up at Columbia University. I worked with him there. He's fantastic. He went out to Caltech, and fortunately we got him back here to Johns Hopkins. Expert on this thing. If you want to know all the true nitty-gritty, he's the one. December 2nd, Joshua Peak has volunteered to give that one, but he didn't give me a title. He just said he's talking about the ISM, which in astronomy, ISM is short for interstellar medium, the gas, the diffuse gas in between the stars. He said he gave this talk in Princeton, and it was an award-winning talk, so I'm expecting it to be wonderful, even though I don't know quite all the details. Finally, in January, we will also have another second Tuesday because the auditorium is going to get retrofitted over the holidays. So what I'm told is we're going to have new carpets and new chairs. I'm looking up in the corner and I noticed some chairs up there that aren't like the others, and I'm wondering if those are prototypes as for what the chairs in this auditorium might look like when you come in January. But when I was trying to schedule this on the calendar, the auditorium was blacked out for 2 weeks, and they said push the PLS back 1 week so that they can make sure the auditorium is pristine and beautiful for you. So January 13th, we'll have a fascinating topic by some amazing astronomer who I will hook into and twist arms, etc. in the next month or two, okay? All right, if you want to find out who that person is that gets the arm twisting, you can go to our website. Here's our Go link, hubblesite.org, Go Talks, or if you just search for Hubble Public Lecture, you should find this page. It has a list of the next 3 upcoming lectures, as well as the archive back to 2005, 9 years of wonderful astronomy talks. This link down here is also the one to go to our webcasting. Our wonderful webcasting team has webcast almost all of the talks dating back to 2005. Let's see, email if you want a once a month or so announcement of what's upcoming Just sign up by providing your email address. We have a good record of no spam. If you want to contact us, send an email to publiclecture@stsci.edu. You can give us a comment, ask a question, or it's a great way to sign up for the announcements because we'll already have your email address. Let's see, for those who do social media, we have Facebook, we have Twitter, we have Google+, we have Pinterest. We may have other things that I don't know about, Instagram or things like that. I do Facebook and Google+ and Twitter a little every now and then, and people sometimes want to follow me. I don't do it that much, so you're not going to get a lot on that. But hey, I'm there just to keep it up. The observatory tonight is not going to happen. Unless you like to look through a telescope at raindrops, you're not going to see much tonight. So unfortunately, you have to come back. Maryland Space Grant Observatory does have open houses with their telescope every Friday night. If you go to their website, md.spacegrant.org, you can find their observatory listed, and they will tell you when their next open observing night is going to be. Okay? All right. So now my favorite time of the evening, news from the universe for October 2014. Our first story tonight, hidden by a supernova. Well, this is a story about the galaxy Messier 81. And this is a beautiful picture of this spiral galaxy from Hubble. All right, you can see it's got a relatively large bulge. It's got a somewhat circular feature around here with the spiral arms tailing off around it. Now, there was a supernova in Messier 81. Messier 81 is actually relatively close by. Okay, it's only tens of millions of light years away, so it's relatively nearby. And we saw a supernova back in 1993. Here's the ground-based image from the Canada-France-Hawaii telescope, CFHT, before the supernova went off. And you see that bright spot there. That is the supernova 1993J. And so you can see that these supernovae are extremely bright. They can be seen at galaxies tens of millions of light years away. Really cool. That makes a supernova studyable across the local universe. Now, 1993J is a type 2b supernova. And I'm not going to explain that in great detail, just it's a massive star, and the presence or not presence of hydrogen lines, etc., is noted in its spectrum. So the idea is that you have two massive stars orbiting around each other, that they are a binary star. One of them evolves to become a giant star, which happens at the end of the lives of a massive star, and material it flows off of the giant the more massive one, the one that evolves first, onto the other one. That star then goes supernova, explodes, and leaving behind a supernova remnant that eventually will fade away, but also the material fed onto this other companion star rejuvenates the star. It adds more hydrogen to its envelope, allows it to get bigger and more and brighter, and sort of rejuvenates that star. This is, I want to say it's like a blue straggler, but you guys don't know what a blue straggler is. It's where by adding new material onto the star, it gives it a new lease on life for a little bit longer. So, seeing 1993J as a supernova explosion, and from its spectrum, determining that it's a type 2b, and this is our idea of what a type 2b should be. So, the question is there a rejuvenated bright blue giant star left in the wake of the supernova? How are we going to tell? Well, the thing I didn't tell you about is that Hubble image is 22,620 pixels by 15,200 pixels, or 384 megapixels. That's a lot of galaxy, okay? That's a lot of resolution. So much resolution that we can go back in there and start searching for the leftover star. Now, for the past 20 years, the supernova explosion, the remnant the gas blown off in that supernova explosion has been too bright. But recently, we were able to look in with Hubble, and can you pick out the supernova? You shouldn't be able to because it's faded away, but you know it's somewhere in here, right? All right. And where I zoom in, one of these blue dots in here is supposed to be the blue star of the companion. Okay? This is the first time that they have been able to identify the companion star left over from a type 2b supernova. All right, that idea, that cartoon that I showed you has been our theoretical model of how these type 2b's must happen. But this is now, we have confirmation in that, yes, there is a bright big blue star left over in the wake of supernova 1993J. It has just been hidden within a supernova explosion for the past 20 years. That's kind of cool. Next, we have Siding Up to Mars, but in the fall, not the spring, which is a convoluted title because I wanted to get the word siding and spring in there. You guys remember? Yes, we have comet sighting spring. I told you about this a few months ago, okay? And I haven't mentioned it since because, well, I'll tell you why I haven't mentioned it since. All right, so this is a wonderful picture of comet sighting spring. Taken in February 2nd of 2014 by a wonderful astronomer. I used a lot of his ISON images too, Damian Peach. He's become very famous for his wonderful comet images. All right, and it's just, hey, it's another comet, right? What's special about sighting spring? Do you guys remember? Well, sighting spring is special. Well, all right, this is a Hubble image of it. I want to show in March of it. So Hubble has actually been taking images of it. Why has Hubble been taking image of it? Because sighting spring is going to pass very close to Mars. Now, this is really crazy because sighting spring is coming in from the Oort cloud. It's way, way out there. It's coming in. And if this is the plane of our planet orbits, its orbit is like this. Okay, so it's coming in, swooping up, and it just happens to have its perihelion close to the orbit of Mars. And it's passing through that point at the same time Mars is passing by, which is really crazy. What a wonderful coincidence. Okay? Sighting spring is going to pass by Mars this month. Okay? All right. And here is the closeness of the passage. This is a scale drawing of Mars, and here is the orbit of sighting spring. They're going to be 135,000 kilometers apart, which in terms of astronomical context, that's a near miss. Okay, I know 135,000 kilometers is a lot to you and me, but on the scale of the solar system, especially on the scale of the Oort cloud, that's nothing. All right, and one way to remember it, it's about 20 Mars diameters, okay? Whereas our moon is 30 Earth diameters away. So this would effectively pass closer, if it were coming past Earth on the same scale, it would be closer than the moon, right? It would pass between Earth and the moon. That's how close it's going to come. All right, but it's 20 Mars diameters. I will also note that Mars's pathetic little nothings of moons, Phobos and Deimos, which are most likely just captured asteroids and not really respectable moons, not that I have opinions on these things, are actually orbiting much, much closer, so it won't be passing inside of Mars's moons. So the question is, as sighting spring is getting closer to the sun, it should be melting more, it should be giving off more gas, and should be developing a larger coma. And the question is whether or not that coma is large enough so that the gas will actually pass over Mars. Will Mars pass through the coma of the comet? Okay, all that gas come across Mars, because then you could see some cool interactions. All right. Well, Hubble has been monitoring, has been looking at it, and this is the normal image from Hubble, and this is the model subtracted image. Okay, so taking a smooth spherical model out of it to try and see if there are jets coming off, because the amount of jets that it's emitting has something will tell us how large the coma might become. And Hubble has monitored it since October of last year. Of course, people have continued to monitor it. Here is one from September 6th, and here's a picture of Siding Spring. Unfortunately, the reports are that it has dimmed in brightness considerably over the past few weeks to months. Okay? So the current view is that the coma isn't really huge enough that it's going to cause a really amazing interaction with Mars. Okay? You could imagine that material from the coma could hit Mars, and you could get aurora, you could get an amazing meteor show, all right? Meteor shower, but we're not sure that we're going to see much, okay? So we're optimistic. It's like ISON. You remember what happened with ISON last year, right? All this buildup, and then, it breaks up as it passes the sun. Well, at least this one we're telling you in advance, hey, it's dimmed a bit. It's not necessarily going to be a spectacular show, but we're going to still watch anyways, because we can get science out of it no matter whether it's a great show, visual show, or not. Okay? Hubble will be watching. Hubble has the finest resolution, so it'll be looking at the comet. Other things will be monitoring Mars, and the most important missions will, of course, already be at Mars. They're in situ. Okay, so we have the rovers on the surface of Mars. But the ones that are really a little more concerned are the ones in orbit around Mars, like Mars Reconnaissance Orbiter and the brand new MAVEN mission that is just arriving at Mars this month. Okay? They need to make sure that if there's going to be a significant meteor storm, that they are protected. Okay? So they have various plans, and they're watching extremely carefully. They will also be doing as many observations as possible. So I can't tell you what's going to happen in, 12 days, 11, 12 days, but scientists are all going to look at it. And what I really hope is that we can get something cool like this with all sorts of meteors crashing in on Mars's thin atmosphere. But stay tuned, we'll find out in 2 weeks' time. All right? Finally, the last story, blood moon in the morning. And what does blood moon refer to? It refers to a total lunar eclipse. This is a wonderful composite picture from our very own Zolt Levay of a total lunar eclipse, where when the moon is in the umbra of Earth's shadow, it becomes red, and hence the name blood moon. All right, this is happening tonight. Tomorrow morning, there will be a total lunar eclipse, and it will be visible for a very short time from Baltimore, but there are a few problems with it. Okay, so here is the timing of it. The partial eclipse starting into the umbra starts at 5:15 a.m. Total eclipse begins at 6:25 a.m. The total eclipse ends at 7:24 a.m. and the partial eclipse ends at 8:34 a.m. If you look at those times and think about it, well, there's one major problem with that. Well, first of all, sunrise is at 7:09 a.m. and the moon sets at 7:11 a.m. So somewhere between here and here, the moon is going to go below the horizon. So you're not going to be able to see it. Furthermore, if the moon is that close to the horizon, you really need a very clear western horizon. Okay? The last total lunar eclipse that I saw, I was on a cruise ship. We were pulling into port in San Diego, and off the back of the ship, we had a fantastic view because all we had was ocean out there to the west. It was wonderful. I don't know of a good place in Baltimore that has a totally clear western horizon. But if you can find one and want to get up early tomorrow, I would say that about 6 a.m., 5:45, 6 a.m., you'll start to be able to notice the partial eclipse. And you'll be able to watch it through till about 6:30 if you can get a really clear western horizon. It's also kind of cool because you're looking out into the west and you're seeing the eclipse of the moon, and then over on the east you're seeing the pre-dawn sunrise stuff coming up. It's just a sort of a magical feeling, all right, looking at that. So if you can find a really cool empty western horizon, please go out and observe it and enjoy yourselves. And dress warmly, bring hot chocolate. That's true for all observing, right? You got to bring hot chocolate for observing. Yes.
There's a five-sided building, I can't remember, I'm so old, the name of it, right at the waterfront.
Okay.
And they let you up to the 30th floor or something, but I don't know whether they're going to let you in it.
So we're all going to invade this building at 5:30 in the morning, right?
It's called the World
The World Trade Center, but will they be able to see the west? Okay? Seeing the east with the ocean, over the Atlantic Ocean is easy, but remember, you got to be able to look to the west. Okay. Anyways, good luck to you all if you want to get up early to do your eclipse observing, okay? All right, I've taken enough time. It's time to get to our featured speaker. And our speaker tonight is Greg Snyder. Greg started his undergraduate work at Princeton. He started, I guess he finished it there too, yes. Then went on to Harvard, where he worked in his graduate work with a friend of mine, Lars Hernquist, one of the preeminent astronomers in computer simulations. And then we are fortunate enough to get him down here. He has worked on one of the most exciting projects in computer simulations and astronomy, and he'll tell you about that tonight. Ladies and gentlemen, Dr. Greg Snyder.
Thanks, Frank. Testing, can everyone hear me?
Yes.
Great. So thanks for coming to my talk, and it's a great pleasure for me to be able to tell you a little bit about the work that I've been involved with the past couple of years. And so my talk is titled, sorry, it's the first time I've used this gadget. It's going to be a couple glitches. So my talk is titled Studying Virtual Universes with Supercomputer Simulations. And that is sort of a shorthand for trying to understand the formation of galaxies in the universe. And so I'm going to tell you a little bit about something called the Illustris Project. And so here's our website down at the bottom, illustrisproject.org. And this collaboration is from these folks listed here and others. And the dry title of a paper that we put out in the spring is called Properties of Galaxies Reproduced by a Hydrodynamic Simulation. And so in my talk, I'll unpack that a little bit and try and describe to you what this means and why this is a challenging thing to do. And so the one word I wanted to highlight here is hydrodynamic simulation. So that just means gas physics. So it's hydro for water, but in the same way, it's sort of modeling the fluids that are important in the universe. So that's where that word comes from. And the main challenge with a simulation like this one is to reproduce galaxies. So the topic of this talk is going to be about galaxies, and here's just a smattering of simulated galaxies that came out of the Illustris Project. So these are galaxies as they exist today, as they might be observed with a telescope like HST, or the Hubble Space Telescope. And so what we see in the nearby universe is galaxies fall into roughly two categories. There are disk galaxies. There are these star-forming spiral galaxies like the one Frank showed earlier. And then there are these elliptical galaxies, which are smoother and redder galaxies. And so the idea is to try and simulate this population of galaxies all at once. I wanted to spend a few minutes to put this in context a little bit, because I know galaxies can be kind of an abstract topic. So first I want to imagine that you're in the solar system. So we all live on planet Earth, here a third planet from the sun. This is not exactly to scale, it's just sort of a toy model of the solar system. So imagine that you're a star system or a solar system like this one. A galaxy is just a collection of 100 billion different star systems. So you can imagine putting our solar system or any solar system in its proper place in a galaxy like this. So if you take the solar system and shrink it down to a size much smaller than even a single pixel of the 38 or more megapixels that may be on this image, it's still smaller than that. And so our solar system is extremely tiny compared to the system of a galaxy. And so a galaxy is now this 100 billion star systems that are bound together by their own gravity. And so this is, say, an image of the light from 100 billion stars that are orbiting around this galaxy over the course of hundreds of millions of years. And so that's a galaxy, and galaxies live in a very large observed universe that we've come to understand over the past couple decades. And I just want to take this a few steps and show you the solar system disappearing there, and this galaxy fitting into its context in the universe. And so this is now a cluster of galaxies of different types, shown with an HST image here. So this is a cluster of galaxies, and I wanted to just highlight where a galaxy like this one, which is not exactly the Milky Way, but it looks like we think the Milky Way looks like, would appear in its context in the universe. And so this is a cluster of galaxies, and here is now what a galaxy might look like inside this larger group of galaxies. That's not all. Galaxies there are hundreds of billions of known galaxies. This is a survey of galaxies, the Sloan Digital Sky Survey, showing you where this cluster of galaxies that I showed you on the previous slide might fall with respect to the so-called cosmic web of galaxies. And so this is what I refer to as the observed universe, and this is what we're trying to understand with our virtual universes in the Illustris Project. And so this is the kind of thing that we're hoping to simulate. And we know frighteningly little about what constitutes galaxies. And so the picture that we've been put together over the past couple decades is one where the content of galaxies is broken down into three basic categories. There's the dark matter of galaxies and the dark energy of galaxies that take up 96% of the known energy density of the universe. We don't know what they are, but we know what they do. So we know exactly how these two things behave in the dynamics of galaxies. In particular, the gravity of dark matter brings galaxies together and holds them together. And the cosmic expansion, which is accelerated by dark energy, moves galaxies apart in cosmic expansion. And these two processes are shockingly simple to model. And all of the hard parts of galaxies happens in this 4 to 5% of atoms which we know about, or which we can model. And so the visible galaxies are, for the most part, along for the ride in this cosmic voyage. But a lot of these visible parts, the atoms that constitute galaxies and stars, is where a lot of the uncertainty and the challenge comes in modeling our universe. And so when we look at the universe, we don't see it in its perfect context like I just laid out. This is an image taken by Hubble of the ultra-deep field. So this is an image taken around 2004 of a region of the sky that's about 1/1000th the size of a full moon. And if you stare at that region for long enough, you'll see all of the galaxies along that line of sight eventually come into focus. And so here's a couple hundred galaxies from a region of the Hubble ultra-deep field. And what I want to point out is that we can see all the way back in time to the beginning of galaxies in these images. So not all the way, but most of the way back, 95% of the way back in time, we can see an image like this. And the reason is that light has a finite speed. It doesn't come to us instantaneously from the very distant galaxies. And so when we take a very deep image like this one, we can see galaxies as they existed many billions of years ago. So these very tiny galaxies, it kind of looks like they're far away because they're smaller, but that is partially true. The very small galaxies in the faint regions of this image, or the faint points in this image, are very distant galaxies as they existed billions and billions of years ago. And so we can kind of work back in time and see how the population of galaxies evolved from an image like this one. And so the visible galaxies, so what we're looking at here is starlight from a bunch of galaxies in the Hubble Ultra Deep Field. That visible light reflects an enormous diversity of galaxy appearance. And so what you see here is that galaxies are not just one shape or size. So even if they are just very simply pulled along by dark matter and dark energy, they can look very different from one galaxy to another. And so that's what we see here. And so we're trying to build a model of this and how these galaxies came about in their amazing diversity that we see in the real universe. And the fundamental challenge, or the thing that we want to understand, is say how a distant galaxy, or a galaxy from early in the universe, evolved to be a galaxy like we see today, like the Milky Way. So if we look at an observation of the sky, or really any survey of galaxies in the universe, we can identify galaxies like these three that I've circled here, but we have no way of knowing how they relate to each other. We just get a single snapshot of the galaxies as they existed at the time we observed them. And so we don't know whether a galaxy that looks like this one, which most of you probably can't even see, it's a little yellow smudge here on the picture, might evolve into a galaxy like this one, which is a blue spiral galaxy that's a little bit closer, and how that might have changed and evolved over time into a galaxy that looks like an elliptical or this smooth red galaxy here. And so we don't have the ability to watch these evolve in time, and so that's why we want to turn to simulations. And so we have this picture we've put together from images like this one of the Hubble Space Telescope observing galaxies in the ultra deep field like this, and we can see them build up over time on average, but we don't know how one particular kind of galaxy could evolve through this space of possibilities. And so the analogy that I like to make about galaxies is that it's exactly, or almost exactly, like archaeology, where we have precisely one fossil record of galaxies that as observed in one particular time in the universe, but we don't know how they lived. We don't know how they evolved to be the way they were. So it's almost like the ultra deep field, or Hubble Ultra Deep Field, is like an archaeological dig site where you're going down layer by layer and you get to see the fossils of living things as they become older and older. So the farther down you go, the farther back in Earth's history you will see fossils. However, you can't then watch how those fossils evolved or lived. You have to put together a story of how they lived by studying them in this indirect way. So I'm going to talk about the Illustris Project in three main points, or three main sections. First, a little bit more background about galaxies and why I think they're fascinating. Then I'm going to talk to you about computational astrophysics as applied to this problem. And then I'll tell you about the Illustris Project and a few other virtual universe projects. So a bit more about galaxies. So I love galaxies, but as I like to say, they have issues. Like all of us do. And so galaxies have a lot of things that make them complicated. So here's a nice Hubble Space Telescope image of two interacting galaxies. And I like to use this to highlight the different challenges we have in that 5% of gas or of atoms that we can understand in galaxies. And that is there's these processes that are really hard to model. So there's star creation. So I'll come back to some of these in more detail, but there's the creation of stars, which happens on very small scales. There's gas and dust clouds, so this is where the hydrodynamic stuff comes into play. There's diffuse gas that fills the interstellar medium. Stars can explode as supernovae, as Frank talked about in his presentation, and those explosions can have an impact on these gas clouds, and so that actually can feed back onto the process of star creation. And so all of these three processes are coupled in some sense, and you can't model one without modeling the others. Another important challenge is we've come to understand that most galaxies have a supermassive black hole at their center. And these supermassive black holes can have dynamically interesting or dynamically important effects on their galaxy. So as this diffuse gas gets funneled into the center of the galaxy, the supermassive black hole can heat that gas and expel it out of the galaxy entirely. And so all four of these processes need to be taken into account, at least these four processes, in order to understand the issues that galaxies have. And then the final thing I want to point out is that mergers and collisions among galaxies are thought to be very common. And so this is showing the two galaxies that are interacting gravitationally, and this process can actually trigger certain effects among these other four that are important. And so it'll shift around the gas and dust and push around the stars and trigger star creation and things. And so all five of these are important aspects of galaxy formation. Arguably the most important and perhaps the most interesting is what I call the galactic life cycle. And so this is just a sort of artist's rendition of what the galactic life cycle is. And I touched on this a little bit in the previous slide, but that is that everything is tied together. So stars form out of gas clouds in the interstellar medium of galaxies. So that leads to star formation in the very centers or very dense regions inside these gas clouds. These regions of star formation then become the solar systems, like the one we live in. But stars have this habit of not being the same for their entire lives. And so they can either explode or shed their outer parts back into the interstellar medium. So I call this star recycling and supernovae. So the stars can then put back the matter that they accreted from gravity in this process back into the interstellar medium and form new gas clouds in the future. And so the galactic life cycle is really the interrelationship between all of these different things. And so if we look at a Hubble image of galaxies, we are basically looking at the light from their stars. But we might miss a lot of these other important processes. Black hole activity. Here's a galaxy showing some interesting black hole activity here. This is a galaxy with very large jets. So this is a radio observation overlaid on top of an HST image showing gas that's being ejected by a very massive black hole in the center of this galaxy. And so if it can get to the center of this galaxy, it'll be accreted or onto this central region near the black hole. And this causes the gas to be heated to extreme temperatures. And that heating can do one of two things. It can either fall onto the black hole and be absorbed and accrete mass, or it can be ejected. So the actual gas dynamics of this process is extremely complicated, but what can happen is the gas goes in and then gets flung out at extremely high velocities and extremely high rates. And so the gas can come out of galaxies and then just not be available to form stars for some period of time. And as I mentioned before, galaxies can interact. So this is Hubble images of different merging galaxies at different stages of the merging process, just to show some beautiful examples of galaxy mergers and to show that this really does happen in the real universe. And so here are two galaxies that may be like the Milky Way approaching each other. They get closer and they sort of tear each other apart as they come to final coalescence. And this can rearrange the gas in such a way that it forms stars in new places, so it can form this very red bulge in the center, a very large bulge or massive bulge, and it can drive gas to the center, to the black hole, and cause more of this gas expulsion in the process. So those are the issues that galaxies have, and now that is the primary motivation for why we turn to computers to do this for us. So if we tried to model all of this by hand, we would be out of luck. We just cannot possibly ever do it. So we use computers to do the dirty work for us. And the way we set this up is fairly nice and fairly simple. The idea is just to start with the initial conditions as we know them in the universe. And so on the left here is a map of the sky made by the Planck satellite. And so I'm not going to talk in too much detail about this, but if you want to hear more, come to Mark Kamiankowski's talk next month. He'll talk, I think, about this issue in great detail. But we take the results of that, which is essentially a map of the matter fluctuations as they were right after the Big Bang. We take a map like that and then seed that as the beginning of our simulation. So we start with matter fluctuations, and then in this example that I'm about to show you, let gravity evolve under its own power. We let the equations evolve as they should see fit. And so we take some initialization of the universe as measured from the Planck satellite, and then just let the matter collapse on itself and form galaxies. And so this is a dark matter-only simulation rotating around a volume of galaxies where each of these points that appear at the center will be a galaxy like the Milky Way. And so from the very beginning of the universe is very smooth, but these tiny fluctuations in the matter density then grow under the influence of gravity to form the backbone or the cosmic web of galaxies that we see today. So that's a fairly straightforward experiment. So this is not sort of done by hand the way we used to have to do this. So we used to have to create galaxies in the computer by hand and then smash them together in some arbitrary way. But this is now a sort of, it's almost a prediction of the universe model that we have. And so we can then very easily test the effects of these different issues on galaxies. Of course, I just spent a really long time telling you about the issues in galaxies, and so that was ignoring all of those things. So ignoring the gas physics and ignoring star formation. And the problem computationally boils down to this fact, is that stars are extremely small compared to galaxies. And so stars form in very, very tiny regions of space, tiny parts of galaxies. And that simple fact means that in order to correctly form stars in a simulation like this one, you have to also model very tiny regions of galaxies and not just their large structure. And so here's an HST image of a dark cloud and a newly formed star, which is probably acting on it via its energy. So the star's feedback energy into the ISM, and it's pushing on this cloud here. And the dynamics of that resulting interaction has to be modeled if you want to actually get the prediction for the locations of the stars in galaxies. And so this life cycle has to be taken into account at each point in the galaxy. And galaxies are at least 100,000 times bigger than that region. So say we have as much computer time as we wanted, as many computers as we could possibly have access to. What would we need in order to do this problem right, in order to model the formation of virtually every star in a galaxy throughout its history during the past 14 billion years? So this is an ideal world, what you would want. You'd want something like 10,000 galaxies, and that's just a nice round number to give you the diversity of galaxies that we see in the Hubble Ultra Deep Field. It's roughly the number of galaxies in the Hubble Ultra Deep Field. And then if you want to divide each of those galaxies up into regions of star formation that are realistic in the sense that I just talked about, you need about 1 million elements per galaxy side. So if you imagine a galaxy is a cube, which is a very simplistic approximation to a galaxy, you need about 1 million elements of star-forming gas per side. And so to fill a galaxy's volume entirely, you need 1 million cubed of these elements per galaxy. So that's starting to get to a big number. And so that's for all 10,000 galaxies, you need 1 followed by 22 zeros of elements of gas dynamics to solve in your computer. That's to do it at a single time. To follow the evolution and formation of those stars in those galaxies, you need to do this at each of about 100,000 times. And so now we're starting to get into absurdly large numbers, and that even though each of these calculations of the effect of star formation in each cell takes a fraction of a second, you still need something like 1 and 23 zeros of computer hours in order to compute the evolution of a galaxy from the beginning of the universe. And just to put that number in context, 10 to the 23 computer hours, on my laptop here, that would take about 10 billion times the current age of the universe to run a simulation like this. So 14 billion years times 10 billion to run it on my laptop here. On the world's best supercomputers, it's about 1 billion times the current age of the universe. Sorry, I got that wrong. It's about once times the current age. It's about 10,000 times the current age of the universe. Sorry about that. So about 10,000 times the current age of the universe on the world's biggest supercomputers that exist, say, in a single room. And it's roughly 1 billion years still on every computer that's connected to the internet today. So there's something like 100 billion or 20 billion devices connected to the internet. If we could run our simulation on that, it would only take 1 billion years to run this ideal simulation, which is still longer than I'm willing to wait for our understanding of galaxies. And so how do we get around this in our lifetimes? Sorry about that. And the answer is we cheat. So we make simplifications and approximations to our equations that allow us to get the gist of galaxies without actually modeling all of the stars. And so the solution is to make approximations. So the first major approximation is to focus effort only on the most important regions in galaxies. So we're not going to focus our effort on the regions that are maybe very low density or have very few stars in them. We're not going to spend as much time on those and just approximate the solutions in those cases. And the second one that is arguably the most important is to create toy models of star formation so that we don't have to model the formation of every star, but we model the formation of stars on galaxy scales. So we can then, so we have these scaling relations that allow us to connect the formation of stars with the amount of gas that exists in a particular region in space. And so we can then chop off our scales in our problem and only model scales above a certain size. And so here's our galaxy with issues on the left, and on the right is how you might divide the space in order to make this first point. So focus only on the most important regions. And so I'm going to zoom in and overlay that on top here. And so in our calculations, what we like to do is to spend less time on a particular volume element over here on the left, or these wide ones over here, and spend a lot of effort in the center of galaxies, where the real action is happening, where there might be more star formation, there are more supernovae, the black hole is in the center, so that's a really important thing to model correctly. And so then we spend a little bit less time, or a little bit less effort, on the outer regions. And so we'll just let these outer regions evolve according to, say, a very simplistic form of star formation and gravity itself. So we just let these things evolve and then actually do some hard computations in the inner regions only.
And how did you come up with that pattern?
This pattern is a certain tessellation of the space. So it's not ideally matched to this galaxy. It's just a sort of a circular thing that I put down to visualize it. But the idea is to break it up into things of the same mass. So a single cell in the center of this galaxy will have the same mass as one of these cells out here. And so that makes it a little bit more computationally tractable to perform. And then the models of star formation is we take one of these regions that we've defined and write down very simple equations for the galactic life cycle. So instead of modeling one of those individual dark gas clouds that I showed you before, we smear that out over the entire region. So this is maybe 1/10 of a galaxy on a side here, kiloparsec or so in size for those who know that scale. And that then we take the amount of gas that happens to fall in that region and then just multiply by some factor, and that tells us how many stars we get in the end. And then we have some other equation that tells us how the supernovae affect the region surrounding that particular cell. And so it's not, we have no idea about the light coming from the stars. So as you can see, the galaxy here, you can see the distribution of stars within a cell. We ignore all that in our calculations. We only have information about, the cell averaged star formation rate. So we can only see sort of like a faint blue fuzz in each of these regions. So that's the approximation we make in order to handle the ability of star formation on scales like this one. And so we won't get a galaxy that looks like this one, that's pixelated on a number of megapixels, but we can get a couple tens of thousands of pixels of galaxies that look realistic. And in practice, this process of creating models, toy models for star formation in black holes is done just by trial and error. So we have no better way of going in and modeling this process other than to say, come up with some educated guesses, see how the galaxies look in the end, and then repeat. So this is a kind of a unsatisfying way to do it, but it's currently the best way that we have of getting a galaxy in a simulation. So our approximations are wonderful, and they help us get this problem to be tractable, but we still need to appeal to supercomputers in order to solve the resulting problem. And so this is the IBM Blue Gene computer with a person there for scale to give you an idea of how big these computers are. So we appeal to supercomputers then to solve the remaining calculations. And so even though we've made these really, really great assumptions that help us to solve the equations in a finite number of universe times, which is great, we still need something like 10,000 or 100,000 computers to do the work for us. And a supercomputer is really nothing more than a whole bunch of regular computers strung together in a fancy way. And so this is the computer that I showed before. Each of these racks, as we might call them, would look like this, perhaps. And so each of these slices in the rack is one computer. So we use it as we would a normal computer. So I just have this down here on the bottom. This is a gateway computer. I had one of these in like the late 1990s or something. So that's essentially what we're putting in here, just a new and updated version and a compactified version into the racks of supercomputers. And so it's really not, it's all the same functionality, maybe a little bit less functionality than a computer like this one, but the same kind of processor would go into this supercomputer and then coupled together to form our supercomputers. And on the left here, I have just a kind of a toy model of how the computers communicate with each other. So I wanted to put this in here just to show that really these computers are all acting as one. So if you imagine that each of these sort of clusters of computers, say 12 computers or so, is labeled A cluster, B cluster, C cluster, and so on up the rack, those are connected by really high bandwidth fiber in between them. And so this is the A cluster of computers here, the B cluster, the C cluster, and so on. And so the entire supercomputer, which might be tens of thousands of these systems, are connected with extremely high bandwidth links, so that in order to get the galaxies on one side to communicate with the galaxies on the other side, they can transmit the information extremely quickly. So at rates that are much faster than you can do over the internet, for example. So factors of 100 or 1,000 times faster than internet speeds. And so in practice, to actually compute a virtual universe like we want to do, I just want to show you how that breaks down in practice. This is a visualization of the Illustris simulation. And to give you an idea of where our galaxies fall that we're trying to model, here is one down here. This is not in galaxy light we're looking at, but this is where it might fit in terms of sizes. So you can see that we might have hundreds or thousands of galaxies in this particular image. The blue purplish light that you see in this image is dark matter. So it's the cosmic web, the matter structure of the universe here. And the red or yellowish tint of the image is something to do with gas dynamics. So this is the gas velocity field. And so this is a way of getting a visual impression of all of these processes acting on galaxies. And so you have the cosmic web of dark matter forming galaxies at the intersections, and then you have this gas being pushed around by black holes and supernovae. So you can see that on the scale of a galaxy, which is this tiny thing here, a few laser pointer widths across, or less, probably less, that there's this really large spherical region of gas that's been pushed out of another galaxy. And so this size region here is several or tens of times bigger than that galaxy itself. So in order to actually compute what happens to this galaxy over time, we have to know what happens at all these other regions of space. So we can't just break these apart and never communicate with each other again. We have to actually have the ability to go back and say, oh, there's gas being pushed onto this region of space by these other galaxies. And that's why we need these sort of high bandwidth links among the supercomputer nodes. And this is now that same grid that I showed you before, but now divided up as you might assign it to different computers. So if you have a supercomputer like IBM Blue Gene or others, you might break up the volume like this, and then assign to the A cluster of computers this one, the B cluster this one, and the C cluster this one. So assign them all the galaxies and actually the matter processes that happen in that region. Let that computer work on it for a while. Same with B, C, D, and so on for a couple thousand computers. And then after each iteration of the equations, you ask, okay, does A need to communicate with B and C and so on? And then transfer the data across those high bandwidth links that I showed before in order to get that information that they need at all the different regions. So that's kind of a heuristic view of what we do to model a virtual universe. I want to spend the rest of the talk just introducing the Illustris Project and what we were able to accomplish using these methods. So the goal, as I've talked about a few times, is to simulate the formation of galaxies. Specifically, the sort of main idea of this was to form about 10,000 galaxies that have roughly the same mass as the Milky Way galaxy. So we live in the Milky Way. We wanted to form something like 10,000 times that particular galaxy size or mass. This is one of the supercomputers that it was run on. This is the SuperMUC computer in Garching, Germany. It was run on another very similar one in France for a time. And so here are the hallways of racks upon racks of supercomputers here. And here's the kind of vital statistics of the Illustris project. And I couldn't think of a much better way to present this, so I'll just give you the numbers. It took roughly 20 million computer hours of total computation to compute the 10,000 Milky Ways and their formation. So it would take my laptop about 20 million hours to compute this. That ended up taking about 6 months on 8,000 computers that were connected together, and it was completed about a year ago in November 2013. There are about 20 billion elements that it ended up being, so 20 billion bits of galaxies that were modeled. And that volume corresponds to about 1 million times the space between the Milky Way and the Andromeda galaxy, which is our nearest massive galaxy neighbor. And the output of the simulation was stored 150 times. So at different cosmic times, we have the history of those galaxies stored 150 times. And that amounts to something like 200 trillion bytes of data that are stored on disk. And I was a little bit surprised that that's only 5,000 iPhones. So if you deleted all your music from your iPhones and put together 5,000 of them, you could store the Illustris simulation on all of them. And I don't know how useful that would be, probably not very useful, but just to give you an idea of how much data there is. And so without much further ado, I just want to show you some visualizations of the Illustris simulation. So these were not made by me, but were made by others on the collaboration. And so this is now the large scale of the Illustris simulation. So each of these bright blue nodes here is where you might form a galaxy, similar to the simulation that I showed before. And this is not going to evolve in time. I'm just going to zoom in and then zoom back out to give you an idea of the different scales that are involved. And so our Milky Way galaxy might reside here, and we're going to zoom into one example of a galaxy. So this is showing just the matter density, and then it's going to change into different quantities here. So then it's going to show gas temperature. So this is the temperature of the gas that might be heated by supernovae or black hole accretion and energy feedback. And so each of these points is a galaxy. This is gas metallicity. So this is the sort of heavier elements than hydrogen and helium that form in stars. And then eventually we go back to stellar light. And so now we're zooming in finally to a galaxy scale, something like that might look like the Milky Way galaxy. It's a little bit more coarsely resolved than the nice HST images, but you can get an idea that this is a nice disk galaxy that might evolve in the same way as the spiral galaxies that we see in the local universe. And we're going to zoom back out to the large scale again, going through gas density now, showing all the companions of the galaxies. So these companions can interact as they evolve in time and have those issues that we talked about with galaxy mergers. And And then now getting to the sort of full scale of Illustris at the very end again, in gas velocity, and then finally in dark matter again. And so we have all this information on scales ranging from the whole universe, or the whole virtual universe in this case, down to the individual galaxies like the Milky Way that we can watch evolve in time. And so speaking of evolving in time, here is now a movie put together by the team, by Mark Vogelsberger in particular, of that evolving in time. And so there's a couple things happening in this movie. One, we're rotating around the virtual universe, which is a little bit unphysical, but it just helps you to visualize what's happening. And the galaxies are evolving in time. So the time since the Big Bang, which you might not be able to read, is at the bottom left. But you can see the galaxies evolve. And at first, all the galaxies were in just dark matter visualization. And now we're adding on top of that some rendering of the gas. And so you get to see pretty cool colors and explosions. I like the explosions. And so each of these blue knots are a galaxy, like we saw in the previous zoom in. There's other things happening now that we can see what's happening in time. And that's these galaxy issues that I talked about. So you can see the galaxies flickering a little bit. I'm not sure how many of you will be able to see that, but there's a small level of flickering among the blue regions in the galaxies. Those are feedback events. So these are these energetic events like stars exploding or black holes accreting gas. So these are pushing energy back into the ISM, and so that's heating the gas and expelling it at high velocities. And that's what's causing that flickering or the explosions that you see. And so those explosions are on huge scales here. So I didn't put a scale on this, but you can see it's, those explosions were plowing through multiple galaxies as they evolved in through the IGM, or the intergalactic medium. So I want to show that again, actually, just to get the explosions again. I really like the explosions.
So Spielberg is hired you?
Not yet. Do you know him?
Are these supernova explosions?
Yes. So I think the flickering, I think, are supernova explosions happening in the galaxies, and the explosions, I think, are energetic black hole events. So the black hole is accreting and then expelling the gas entirely out of the galaxy in those red explosions. And so this is largely just visualizing the gas, so the gas dynamics of galaxies, which we don't actually get to see when we look at a galaxy with Hubble. So all of the very beautiful Hubble images of galaxies that we've seen show primarily the stars, but we don't get to see all of this action happening in the galaxies with an image like we get simply out of Hubble in the Hubble Ultra Deep Field or surveys like it. And so we really like to have these simulations to get at that aspect of the science. So we don't actually get to see this happen very often in the real universe.
Well, in this movie, you're running at about 500 million years a second as we're looking.
That's right. Yeah. So that helps.
Hubble is static, basically.
Of course. Yeah. So we can then see how things evolve in the simulation and see if it matches what we see in the real universe. And so that's great. So now we have all the pieces we need in order to put together our story of the evolution of certain galaxies in the simulation. And so now we can take our simulation and identify galaxies at different times and then see how they evolve into the galaxies that we see today. And we can watch them happen one by one and track them and see what happens and sort of tell each galaxy's story by itself. And so in the end, I showed you a couple of neat visualizations of the Illustris simulation. What you get are galaxies like we know and love in the local universe. And so these are simulated galaxies from the Illustris simulation, just fewer than 20 of them shown on a slide. These were selected visually just to show you the sampling of disk galaxies and elliptical galaxies that we get in the end. And this was the ultimate goal of the Illustris project, to get this sort of separation in the galaxy types and to sample the different types of galaxies that we see in the universe. And I think we've accomplished that. We've gotten to that point. But with a simulation of this scope and this size, we have, I think, access to a lot more power in the future. So let me just talk a little bit about where I see this going. And the specific example I want to show is a model of the Hubble Ultra Deep Field. So on the left is the actual Hubble Ultra Deep Field from the observations made by the Hubble Space Telescope. And on the right, you're looking at the Illustris simulation in exactly the same units as you would observe them in a Hubble Ultra Deep Field. So I've taken that simulated volume and then observed it with a Hubble Space Telescope in the computers, basically. So it's an imaginary Hubble Space Telescope, drawn a line of sight through the box in the Illustris simulation, and then at each galaxy point, decided how it should look according to the Hubble Space Telescope's filters and cameras and things like that. And then just rendered that in the same size, same region of sky as the Ultra Deep Field. So here is 10,000 galaxies observed in the universe. Now we have 10,000 galaxies mock observed in a mock universe from the Illustris simulation. And the Illustris simulation is one of several collaborations that have finally reached the point of being able to do this kind of rendering. It has never before been possible to populate a Hubble Ultra Deep Field with galaxies that are simulated from the beginning of the universe. And so this is really a first in theoretical astrophysics. We've been pushed along by observational advances like the Hubble Ultra Deep Field for 30 years now, and we've only just caught up to the sort of Hubble Space Telescope-like surveys of galaxies in our simulations of galaxies. And so that's sort of representing this slide is representing of that fact, that we've come a long way, and we finally can have a mock universe to call our own, as it were. So I'm going to zoom in here on the real sky. So this is similar to the one that I showed earlier in the talk of the Hubble Ultra Deep Field, showing the diversity of galaxies as observed directly with Hubble. And I'm going to slide over slowly to the simulated side. And you can see where the transition happens here. And these are now entirely a simulated universe. So you can see a nice diversity of galaxies of different colors and shapes. And yeah, so this is sort of a mock observation of the Illustris simulation itself here. And so you can see an elliptical galaxy up at the top, blue star-forming spiral galaxies all around, and so on. Now, it's not perfect. So I don't want to claim that it's perfect, and I think we have a long way to go to actually get it to look more like the Ultra Deep Field. So I'm going to jump back and forth now quickly. Here's the Hubble Ultra Deep Field again, and here's the simulated sky of the same size, in the same units. So you're looking at the same rendering, or the same colors are the same. But galaxies are a little bit bigger in the simulation, so the galaxies are much larger, maybe a factor of 2 or so than they are observed. And the colors are a little wonky, so the colors are not perfectly matched to the real sky. And we think we have now the ability to take this information and then improve our models of virtual universe formation. So what this allows, now that we can populate things like the Hubble Ultra Deep Field and other surveys of galaxies with fake galaxies, this allows us to make a statistically robust comparison against observations across all of cosmic time. So this is a quote that I really like that was in the CNN article about the Illustris Project by one of the team members, Dylan Nelson, who's a graduate student at Harvard. And so this is kind of a long way of saying we get a lot of galaxies. So we get a number of galaxies that we can then statistically compare with the real universe and then iterate again. And so the next model universe will take the lessons we've learned from that statistical sample, which we have for the first time, and then iterate and create better ones. But I want to end on the note that quantity is not everything in this. And so the quality of the galaxies you get out is also something that people are modeling and trying to get at. And in particular, there are other groups simulating galaxies that made different choices about how to handle the issues of galaxies. So I described one example, the Illustris simulation. There are other groups, and including our own group, which are taking different choices for how you model star formation. And what that lets you do is, say, trade away the statistics for higher fidelity images of galaxies. So you can get a better handle on the formation of stars within galaxies rather than the formation of a population of galaxies. And so I just want to show a couple examples of that here. So this is a simulated galaxy. On the left, as it would be observed with HST, if you could observe for a long period of time, we would see this. But the simulations now are getting to the point where we can go beyond what HST is even capable of. So the fidelity of the simulations, this one is not the Illustris simulation, goes well beyond what you can do with HST. So HST, which is a 2.4 meter mirror, can only resolve so much. And so the resolving power of a telescope is directly proportional to the size of its primary mirror. Here at 2.4 meters, a galaxy that's 3 billion years old, or 3 billion years after the Big Bang, will be largely a smudge. And so all of the interesting stuff that I talked about, the issues that are involved in galaxies, the formation of stars, are smeared out along these big regions. And the simulation of galaxy formation can now go well beyond that. So here's a rendering of a 16-meter telescope. So imagine if you could take Hubble and make it 16 meters and put a big camera in it, and you get an image like this one. So this is a very distant galaxy, one of those little smudges on the ultra-deep field that I showed. A telescope like this one could resolve all of them into its constituent parts. And we could see all of the interesting bits of galaxies here in the observation. And so this simulation is one galaxy. We don't really know how to say anything about the statistics of galaxies, but we can start to understand where our place in the universe really is here. So I showed you before where our solar system would fit in a real image of a galaxy. With the simulations that are coming online now and the possible future missions beyond HST, we might be able to start to see the regions of space where our solar system formed in model universes, in virtual universes like this one. We're still not there yet, but I think in the coming decades we'll be able to get there. And so this is an image of some of the missions that NASA has launched and is launching and may launch in the future. So here's HST, which was launched in 1990. And I think we've just caught up with HST's ability to observe the universe with our virtual universes. So we've finally gotten back to the 1990 era galaxies that we can observe with HST. JWST will be launched. The James Webb Space Telescope is currently being built down in Goddard Space Flight Center in Maryland with a planned 2018 launch. So this will then set the bar even further for our models of galaxy formation. And the one that I showed you, the mission concept that I showed you, is one that's currently being discussed by some scientists here at Space Telescope. It's called the Advanced Technology Mission Concept, which could have a 16-meter diameter mirror and would give you those perfect images of galaxies that I showed on the previous slide. It could also observe an Earth around another star directly. So it has a couple different things going for it. So in addition to resolving galaxies, it could take a picture of an Earth orbiting a star in our galaxy. And so then just to summarize that, here's an HST image of a galaxy 3 billion years after the Big Bang, a very distant galaxy. And here's how it would look according to a 16-meter telescope. And so we can actually begin to resolve the bits of galaxies that HST is revealing to us into the regions of space where stars like ours formed in the past. And so then I'll just end with a movie of that particular simulation evolving in time, showing HST on the left, JWST on the right, and then two sort of toy models for telescopes that could exist in the future. It may be a little bit hard to see in the back, so feel free to come up afterwards and take a look at this, or look at these screens, which might be a little bit crisper, that the 16-meter telescope and 8-meter telescope really resolve the fine bits of galaxies that you don't get to see in HST. So the fine structure, internal structures of galaxies, where the stars like ours formed, is revealed in a telescope like this one. And so that's the end of my talk, and I'll end there. Take any questions you might have. All right, up here.
It isn't a fair question. It's about money. I'm looking at the German supercomputer, or at the GE supercomputer, or IBM supercomputer, and you showed 8,000 computers.
Yeah.
And 6 months.
Yeah.
And I can't even think what it must have cost to use that German supercomputer for 6 months.
So I computed this once. I calculated how much the cost of it was. And luckily to the scientists like myself and Dr. Summers and my collaborators, it's virtually free. So the supercomputer centers actually have a really strong need for problems that can run on their computers. So they have calls for proposals from scientists who want to do these big projects, and they provide a little bit of support and hand-holding to get us up and running on them. And so it's the supercomputer centers who are investing all the money, and the governments are investing the money, and it's not coming out of NASA's pocket, which is nice.
Recognizing that these supercomputer centers exist not to do astronomy actually, but they exist to solve problems in computer science and how to do even better computing. And so they love astronomers because we can, as we say, as you build a bigger supercomputer, we can fill it with more astrophysics.
Yeah.
You said there's 8,000 computers in that German thing? Okay, in 6 months with 8,000 computers, you got about 35 million computer hours.
Yeah.
Well, you said 20. Do they only do you at night or?
I was estimating, so I was a rough approximation of the number of computer hours. But there's also, I made it sound like it was all easy. It ran in 6 months, but there were problems. The computers crashed every once in a while, and so we have to use a couple million CPU hours and then start over and redo it. But to answer your original question, so the primary cost to use a computer once it's built is in electricity. So the vast majority of the money for this project was spent on electricity in Europe. So generating electricity in Europe for the computer was something like $5 to $10 million in total during that computation.
How many such computers are there in the world?
I looked this up for this talk. Maybe 100.
Yes.
Some of similar scale. No more than that.
I mean, I know it sounds huge to the general public, but a cluster of 1,000 CPUs is nothing these days. Sorry, when you're talking high-end supercomputing, they can put lots of cores on one die, and then lots of chips in one slot, and lots of slots in one chassis, and lots of chassis in one rack, and lots of racks in the room. And just think of what Google has and other internet companies in terms of their racks. They're going to dwarf these things.
Question in the back.
So is your standard for evaluating your models essentially the spatial distribution of stars and mass and light and gas? Is that how you're judging how good the model is?
That's what we hope to do. What we have done in the past is focus on more global quantities about galaxies. So galaxies have so many issues that we have not even been able to get the star formation rate of galaxies simulated correctly. So we're only now just at the point where we can start to talk about where the star formation is happening within galaxies, so spatially resolving that star formation. So our metric for creating the initial simulation had nothing to do with the shapes of galaxies. It had everything to do with the amount of stars in the galaxy, basically. And so once we got to that point, we said, okay, let's run a simulation and see what we get. But now that we have all of this data from this simulation and maybe half a dozen other simulation projects with similar amounts of data, what my research is now actually is to take that information and ask, what is the new metric? Can we now write a metric that takes the shapes of galaxies into account and the spatial distribution of light in the individual galaxies into account? But we don't do that yet. It's still in the works.
You talked about the common frequency of the interaction between galaxies. So in this simulation, are you able to determine how that may have changed over time with the expansion of the universe?
Sure, yeah. So there are members of the collaboration literally calculating the number of interactions between galaxies and mergers of galaxies. And today, the rate is very low. So in the current universe, as the universe expanded, things grew farther and farther apart. Galaxies are less likely to merge now than they were in the past. But yes, in the past, the histories of these galaxies are filled with mergers in the distant past. And many of them happened when the galaxies were infants, basically. So the galaxies were really tiny when the mergers were happening. So you may not be able to see those grand mergers in the distant universe, but they're going to be really tiny things that are very faint and hard to detect. So it's the interactions they're hard to see in the real universe, and so we can simulate them, but we won't be able to test it until things like JWST come online. Yeah.
How thorough is your gravity? You got relativity in it?
No.
All this other sort of stuff?
Gravity is basically as it was in 1700. as it was understood
Based
by
on
Newton.
gravity.
Yeah, so very
Recognize its approximations, and you can do scale order calculations to see whether relativistic effects are necessary compared to other effects that we're using for approximations, and they are second to third order in the computer simulations. So you take your first and second order effects, and you'll go further down the chain as time becomes available, but they aren't necessary. Those corrections aren't necessary.
Those corrections are certainly important for modeling the black holes at centers of galaxies, which we don't do. So we made a toy model for that. So we basically cover up all of that general relativity stuff in a toy model, and so we don't directly simulate it.
There.
Yeah.
What's the long-term goal of perfecting these virtual universes and the context that it has in the larger astrophysical community? So are you hoping to actually discover things via simulation that we haven't been able to observe?
Partly, yes. So I think a lot of it has to do with being able to understand the data we already have. So we have this enormous diversity of galaxies in things like the Hubble Ultra Deep Field and other HST surveys, but we don't understand it. We don't know what any particular shaped galaxy means at a particular time in the universe. So we have to make these models of things in order to basically read between the lines of what is happening to galaxies. And so we're going to maybe not discover a new phenomenon, but we'll discover a phenomenon and then say, hey, we can test that now with our telescopes. So we're going to have these phenomenon that we had no idea were interesting. So we can see them in our surveys, but we can't assign anything meaningful to them until we have a simulation like this one. And so that's the basic idea. We can look and then say with some better confidence what we'll expect to see in a different survey. So basically being able to go back and say, okay, now we want to look for something else, look at a different wavelength of light, so on and so forth in that respect. So not necessarily discovering something brand new, but.
All right, but let me just give some old geezer perspective, because when I was doing my PhD simulations, et cetera, a lot of what we were trying to do was help pin down what the basic structure of the universe was. Was it cold dark matter? Was it warm dark matter? Was it, was this crazy idea of a cosmological constant even to be taken seriously? And the simulations could show you the distributions of galaxies in these various cosmological models, and that led us towards a flat universe that eventually, over the past 2 decades, we've come up with a concordance cosmological model. So he has this Illustris simulation has the benefit of really having a well-defined, relatively well-defined cosmological model in which to do the computations, and so they can get down to the nitty-gritty of what types of galaxies form. What are the details of them? How quickly do they form? I mean, when we can't see the development of galaxies over the first 3 to 5 billion years, you can give predictions as to what you should see and whether or not telescopes should be able to see some of these ideas.
Yeah. Yep.
You showed us 4 pictures. I'm sorry, I saw it. I can't remember 10 minutes ago. 18, 16 meter, 8 meters. Are those pipe dreams, or when would that come?
So that's a good question. They're currently pipe dreams, yeah. So they're currently being discussed among the astronomy community as things we might want to think about after HST and JWST.
What is JST?
Sorry, I said it really fast. It's the James Webb Space Telescope.
Yeah, but what's its?
6.5 meters.
6.5. Well,
yeah.
So 8 isn't too.
It's not too far off. There's another issue that I've glossed over here, and that is that the James Webb Space Telescope is tuned for different wavelengths of light than is the Hubble Space Telescope. And so the large mirror on James Webb will not entirely go to resolving the bits of galaxies as well as these future concepts might. So these 2 mission concepts are tuned to blue light like HST is. And so in blue light, you can really resolve the features of galaxies more clearly than in infrared light, where the light gets smeared out. Even with big telescopes, the light gets smeared out to a point where it's quite similar to HST resolution, actually, in the end.
But the fact that JWST is a multi-mirror telescope in space, 18 segmented mirrors, is the precedence for having very large multi-mirror telescopes in space. And what we learned from JWST will definitely help us get towards these 16-meter multi-mirror telescopes as well.
and you're shooting up a very large structure. The stresses on it are so much bigger. What did you say the JW is? 5.6?
6.5 meters.
6.5, 36 and 8. That's twice.
Yeah, it's pretty big. It does fit in the sort of next generation heavy launch vehicles that NASA is considering building now. So that it's not totally outside of the realm of possibility, but it's hard. It is going to be hard to do something like that. And then I think I didn't end up answering the timeline question. It would be something like the 2030s, something like that would exist at the earliest. And so when James Webb was dreamed up, we thought it would be, what, 2000? 1995? I don't
For
know.
so many years, it was 2012, and then it was 2014, and now it's
Yeah,
2018. It
2018.
just,
So it's where James Webb was 20 years ago, basically. So it could be 20, 30 years if we are able to obtain funding for something like that. Questions?
Who's paying for this space program now?
Taxpayers, so you and I, largely. So it's the U.S., largely the National Aeronautics and Space Administration, NASA, the European counterpart, who collect tax money through the government and then pay for it through public
There's no
funds.
space program per se, it's just, this is like Johns Hopkins University right here.
No, there's a space program. There is not a manned space program currently in the U.S. So we're not sending our own astronauts with our own spacecraft. But there are these.
The man one has stopped. Okay.
Yeah, so we have these are all robots now. So we have a robotic space program essentially, and for the purposes of astronomy, a lot of this can be done robotically.
right. And just for perspective, about 1/2 of a penny out of the per dollar of the U.S. budget goes to NASA. It's not a lot. There's a question way up in the corner.
I just was going to ask if those launch dates are predicated mainly, as we were discussing a moment ago, about is it technology, or is it the funding considerations? Both, as far as when you're setting these possible launch dates, when we talk about 2018, and apparently it sounds like it's more of a funding matter.
I would say it's all of the above. So if you were given an infinite number of dollars right now, it would still take some time, I think, to create something like this. In part because all of the people who have expertise in telescope design in space are currently working on James Webb Space Telescope. So it's actually people power that you need people to work through the technological challenges and sit down and actually engineer something like this. And so I think, it's a combination of these things. We need the money, first of all, to pay the people to do the work. But the technology seems, once it's written down and once it's been thought up as a possibility, it's largely just working through the details, which I'm glossing over a lot of stuff, obviously. But I think many of the major challenges are being overcome with the James Webb Space Telescope. So this advanced technology mission concept doesn't have any major sort of technological barriers. In fact, it has fewer technological barriers than James Webb did when it was brought up, because it's not going to work in the infrared. And so that helps a lot in terms of the technology development.
And just to put in perspective, what became Hubble was first discussed by the National Academy of Sciences in 1962 or 63. Okay, so having a pie in the sky idea can take decades to come to an actual telescope. All right, any last questions? All right, let's see. Let's see, it's October. Next month, November, Mark Kamiankowski, second Tuesday of the month. And everybody, let's give a great big hand for Greg Snyder.